Hi, my name is Joe Rumsey. I'm a principal software engineer at Blizzard. If you're wondering what principal software engineer means, it means when other programmers are misbehaving, they get sent to my office. Not really. So I've been at Blizzard for the last 12 years. I was the lead server engineer on World of Warcraft, and I'm currently working on Blizzard's next-gen MMO. Today I'm going to show you Jam, which is the application-level network library we use for World of Warcraft and our next MMO. So yeah, I named it after myself. I'm sorry about that. It was an accident. Jam's a network serialization and transport library used by both of Blizzard's MMOs. There are similar projects that are widely available today, such as Google Protocol buffers, but Jam development dates back to 2001 when there weren't any good alternatives. Today, I think Jam stacks up pretty well against the ones that do exist. So I'm going to outline the why and how of Jam and why we're still happily using it today. Hopefully, some of you will be inspired to create something similar for your games, or come work for us. We're always hiring. And at the very least, I hope if you're not using something like Jam already, you'll decide to check out Protobuf's, Thrift, or another similar tech. So when writing an MMO, it's a given that there will be multiple servers and types of servers involved. All these servers need to talk to each other. The resulting system can be quite complex. So we need systems that let us manage that complexity as simply as possible. I'm going to demonstrate the core systems that World of Warcraft uses to mitigate that complexity. We'll see code that automatically serializes both simple data structures of flat data as well as dynamic types, code that tracks and manages connections for us and does all the above easily and efficiently. At the time WoW shipped in 2004, Jam was only used between game servers. Today we also use it for internal tools, and in current Blizzard projects we use it between game clients and servers as well. Today's talk I'm mostly going to focus on the inter-server communication. Many of you probably serialize your network messages manually, because if it was good enough 20 years ago, it's still good enough today, right? This is what your code might look like without Jam or some library like it. For anything you want to send and receive, you have to write both ends of that code. And this code has a bug. Have any of you spotted it? The loop iterator has an off by 1. You might have found that one pretty easily, but if it was buried in a more complex message and they were in 2 separate files, you might have had a much harder time. You shouldn't have to spend your time looking for things like this. If it's subtle enough, you might not find this error until your game went live, but more likely you'll spend hours debugging your message passing when you could be making your game awesome. Programming errors like this were exactly the first thing Jam was created to avoid. So if you're writing a chat server, you can probably get away with serializing your data manually. If it's a checkers game with chat, it still probably won't bite you in the ass. And by the way, PR told me no way, but I said, screw that. I got to give them something at GDC. So I'm going to announce it right here, right now. Blizzard's next MMO is actually World of Checkers. There you go. So our Checkers MMO has thousands of pieces, and each of those pieces has dozens of attributes. Not all the pieces can see all the other pieces. Parts of the board are on different servers. Pieces can be added and removed dynamically. Some pieces have scripts that control their behavior. Crazy special checkers attacks have to work with all of that. Suddenly, there's a whole lot of complex data getting passed around. Your code works fine for a while, but then one day pieces start changing color inexplicably. You somehow screwed up your message passing, and it's going to take days to track it down. All right, I like code that's bug-free. Even more, I like code that doesn't let me write bugs in the first place. Dry or don't repeat yourself is an oft-repeated acronym among programmers. The idea is that if you have to write the same code more than once, you will create more errors. Reducing the amount of code you have to write to accomplish a task also reduces the number of bugs you have to find later. Anytime you find yourself writing the same code or similar code over and over again, you should stop and figure out how to write that code just once and be done with it. I'm going to outline a couple things we've done to automate the repetitive parts of network programming. One of the problems Jam was originally created to solve was errors due to hand serialization and deserialization of data. It's bad, just don't do it. Jam isn't the only way to automatically handle that, and I'll give you some open source alternatives to doing it yourself. But no matter what, don't do it by hand every time. Constructing messages is only part of the solution that Jam gives us. We also need to be able to get our messages from one place to another. I'll show you how Jam manages our connections for us. Protocols and routing are mostly boring. We're here to write games, not tell stupid computers how to tell other stupid computers things. Figuring out what information needs to get from one place to another is our job as programmers. We should be able to tell our computers the bare minimum they need to know in order to let them do that and let them figure out the hard parts. Computers are really good at doing boring stuff. Put them to work for you. So JAM gives us a helpful robot that writes code for us. Using JAM, we describe a protocol using familiar syntax. From that description, we generate code in C++ and other languages to handle serialization. Our message handlers are well defined, and adding a new message is as easy as declaring a new structure. Connecting to remote services is simple and is managed for us as much or as little as we want. JAM leaves us free to concentrate on the parts of our games that matter and does so with little cost in bandwidth or processing time. All right, so this is how we really want to write our protocols, right? There's a structure definition for our message, which has structure definition, and then there's a simple declaration of an instance of that. We fill some data in, and we call send. All of our communication should be that easy. When we need to send another program a message saying a checker has been captured or a monster has been killed, the message should be a structure named checker captured or monster killed, with a field saying what checker or monster it was, who captured it or killed it, and anything else the receiver might need to know about it. There should be a simple structure per event that needs to be sent, and sending one of those messages should be possible using nothing but standard C++. When we need another kind of message, we write another structure definition and we're done with it. The receiving code should be a function that gets a pointer to one of these whenever another program decides to send us one. No messy serialization details, no chance anyone's going to parse it incorrectly. Computers are good at figuring this stuff out, and we should let them. All right, so that's it for the theory. So now let's get into the meat, how we actually do this. So there's 5 steps to creating and using JAM in an application. The first is to describe a protocol, so let's go through that first. This is a sample JAM message definition. It looks a lot like a plain old C struct on purpose. A JAM protocol is really just a bunch of these message definitions in a JAM file. All the data members that we put in JAM message definitions have a direct correspondence to members in the C++ structures we generate. That might sound obvious, but it's important. If you look at a JAM file, you know immediately what the structures are going to be named, what the fields in those structures are, and how to write message senders and handlers for them. Also, from this file, you know what the protocol is going to be named, which will be important later when setting up our program to send and receive them. If you do need to see the actual code, we try to generate code you'd be mostly happy to have code reviewed by your peers. We can see here that our message definition is turned into a class with the same name that inherits JAM message. JAM message is an interface class that implements virtual methods for serialization and other things we might like to do with a generic message. All right, so the next step after describing a protocol is to run that description through a code generator that generates a bunch of serialization and dispatch for us. All that ugly serialization code we saw before is now generated for us in the output from the JAM parser. Given a binary encoder object, which is basically a stream object, any JAM message can serialize itself to that stream. Then later, using a binary decoder object with that stream as input, a JAM protocol can create and dispatch an instance of the C++ message classes we saw previously. With all those capabilities, we now have enough to implement a simple network protocol. That level of payload serialization is as low level as I'm going to get in this talk. The assumption is that you have encoder and decoder objects that can deal with simple data and a transport layer underneath to send it over the wire. JAM generates the code to serialize a message using an encoder. An encoder creates a raw stream of bytes, and a transport layer gets those bytes where JAM tells them to go. Later, I'll talk about how we negotiate which protocols to use over a given connection and how we route messages, but the actual transport and encoding are out of the scope of this talk. So far, we've seen a JAM message and some of the code generated for that message, but if you haven't seen something like this before, you might be asking, hey, Joe, how do you get from a JAM file to C++ code you can actually use? Thanks for asking. I really appreciate that. A really long time ago, some really smart people created some programs to help parse structured languages. Lex and Yak, or their GNU replacements, Flex and Bison, are probably the best known of these. More recently, there's also Antler, which you might look into if you're setting up something like JAM. I use Flex and Bison because they work really well, and I've used them lots of times before. But all of the tools listed here offer way more power than you're likely to use, and I don't think you can actually go wrong with any of them. If you're new to it, Antler and Gold both include GUIs that might make it easier to get started. And if you go with Flex and Bison, the O'Reilly book is really a great place to learn them. So Flex and Bison are hard to adequately describe in this talk, but the quick description is that they let us very clearly describe the syntax of a JAM file in such a way that we can load the contents into a format we can work with easily in code. When we load a JAM file, we get a syntax tree representing the metadata of all the messages in the file. We can then iterate the messages, get the fields out of them, and retrieve other attributes for various things that are in the JAM file. So we've essentially created half of a compiler, the parser, for half a programming language, the data definitions. YAC stands for yet another compiler, and this is exactly the kind of thing it was intended for. YAC or Bison, which are really the same thing, and JamGen, the program that the parser gets compiled into, have a lot in common. They both exist to make up for shortcomings in other programming languages that were causing their creators pain. Both take simple inputs and produce output that would be tedious or difficult to produce by hand. All right, so this shows the basic flow of how we get from a JAM file to a CPP file. First, we load a representation of the JAM file into memory using Bison. Then we turn it into C++. So how do we do that? Back when WoW shipped, JamGen just had a bunch of code that walked all the structures in the parse tree and fprintf'd it to files. Sure, we had fancy macros and helpers and so on, but that's all it really was. That worked up to a point, but as things got more complex, it got harder and harder to change the output code. Then we started writing more tools for other problems that needed to do similar things. So that's when TRL was born. TRL is the template replacement language. JamGen loads a JAM file, puts all the data into a dictionary, and hands it to TRL. So this is what TRL's input looks like. In this case, it's a template to generate C++ code. Every JAM message we put in a JAM file gets run through this template to produce the generated message class. It's a little bit ugly, but it's a whole lot better than a bunch of printfs. And if you're interested in this sort of thing, TRL was originally inspired by Django's HTML template language. For ready-to-use C++ library, Google's C template is similar. And there's a pure C NG template. And then when I rehearsed this talk at Blizzard, someone told me we're actually using Jinja for some things internally, which is another Python standalone template library. So now that we've got our syntax tree and a TRL file that looks vaguely like the code we want to produce, what's next? It's easy. Walk the syntax tree and fill out a string-based dictionary containing all the relevant data. Hand that dictionary and a TRL file name to the TRL library, and it'll spit out our output file. All templating engines work basically that way. C template or something like it should work just fine. The code that builds the dictionary is simple. It just has a linked list of messages which it iterates, and for each message adds a list node to the messages key in our dictionary. In each node, it adds the name of the message and some other metadata. Then it adds a list to the message which has all the fields of the message. So on the previous slide, we saw the TRL code. We saw TRL code that iterated the fields of the message and added default values to the generated constructor for each field that has a default value. That's it up there, and you can see that besides the simple replacements in the middle, TRL also has some simple control structures. In fact, that snippet up there contains about 3/4 of all the language features we have in TRL. The only thing it's really missing is function calls. So when we need to make a change to all messages, it's easy now. So say we had originally decided that checker ID was a byte because 256 checkers should be enough for anyone. Since checker IDs are used in virtually every message in our checkers MMO, we built checker ID into JamGen as an actual type that's really just a type def to a uint8. Later, though, we realized that 256 is not nearly enough checkers for an MMO, and we need to change it to a U16. If we were hand serializing all of our messages, this could be a disaster. But since we're not, we can just change a few things in JamGen, or likely even just in our TRL, and suddenly we've fixed all of our protocols. This is a bit of a contrived example since we don't generally add special types to JamGen itself, but the idea that we can make changes to many protocols at once holds. On the slide, you can see an actual change, an actual diff, where we added the ability to compress JAM messages. So there's a little bit of extra handling needed in our serializers, which we got automatically for all messages by writing the code once in our TRL file. So that 2-line diff up there would have replicated this change across dozens of protocols and hundreds of messages. All right, so we've described a protocol and we've generated code for it. So now we're ready to actually start sending some messages from our application. So this is how a jam message gets sent. A simple instance of the checker captured credit message is declared. I wish I'd come up with a less awkward name for this example. Next, we put this checker, the one that just got jumped, into the captured checker ID field. Since we know who jumped this checker, we put that in the message too. And the last bit of data is what type of jump it was. You know, like a regular jump, a double jump, or a critical jump, or a special ability jump. The destination credit manager is a jam ID, which is really just a 128-bit address, which can define either a service or an object. Later, I'm going to show alternate ways of sending messages to service types rather than specific services, and how we send messages directly to objects, too. For the most part, jam IDs are opaque to application code, though. You can compare them and copy them, but the contents aren't important. Each individual jam message is just a structure. When it's time to create a message to send, all you need to do is declare an instance of one and fill out the data. It's simple C++, practically simple C, and there's nothing hidden going on in this code. Though this message, like most messages to be sent, is declared as a local variable on the stack, there's no reason we can't allocate it with new or make a pool of messages or any other allocation pattern we want to use. There's a few high-volume uses of jam where we do things slightly differently just to avoid the small construction and destruction overhead, but 99% of the places that send jam messages look just like this. So far, I've only shown simple types as data in jam messages, but jam also allows us to use dynamically sized arrays in messages and structs and arrays of structs. So originally, struct support was just the ability to use any C++ class that implemented serialization methods. That method still works for protocols where only C++ output matters, and we do occasionally output other languages like C# and Python. But we have a better way now. We have a reflection system for generic non-message data called structgen. The structs it outputs are also used by things other than just jam, like our database and asset layers, which is why it's not just part of jamgen, too. Structgen is built using TRL just like jamgen, though. The structures that jamgen outputs and arrays of those structures can be embedded in jam messages just like plain old data. So on the upper left, you can see that I defined a message named group update that contains a group ID and an array of checker IDs. On the upper right is the data section of the generated jam message definition containing a standard vector of checker IDs. And finally, on the bottom, there's some code that fills in that message, resizing the vector first. We don't actually use STL, but why not is really way outside the scope of this talk. So if you see anything that doesn't look quite STL, it's because I screwed up making the examples. All right, so before I go on, let me make sure I've defined some terms I've used a lot. A message is a serialized structure defined in a jam file. A protocol is a collection of messages. A service is a module of code that implements message handlers for one or more protocols. And a program can be composed of multiple services. All right, jam provides us with several different ways to send a message. Sometimes we know the jam ID of a specific service we're connected to. We can call a send method with that jam ID and a message pointer, and it will get there. Sometimes all we know is a type of service, and we want to send a message to any service of that type that we're connected to. We can do that too. We can also broadcast a message to all connected services of a specified type. In some cases, we have a lot of different objects, checkers, for example, that all live within a larger service. So we can also send messages to the individual objects. And if you're looking closely, you'll see that the third example is sending to a checker ID rather than a jam ID. They're related types. They're both 128-bit IDs, and services that use objects as destinations can use a checker ID as a destination just as easily as a jam ID, as long as the receiver provides a way to resolve a checker ID to a checker object in its dispatcher. I'll show a little bit of that in a minute. Until the last couple of years, most of our messages were sent to specific jam IDs, either services or objects. Jam provides link up and link down notifications from which we can retrieve jam ID addresses. As we started implementing more and more services and tools using jam, we noticed there was a similar pattern to many of them where they would watch for a service of a specific type, store off the jam ID whenever they saw the first one, use it until they lost connection to that service, then find another service of that type and start over. That code was really easy to screw up, and we kept finding subtly different ways to do it wrong. So we added the capability to jam to do two things for us. First, it will track service connections of types we've tried to send a message to, so that we can just tell it to send a message to a service type rather than a specific instance. And second, it has a message queue that gets used only if there are no valid services of that type. That way, we can now send messages even before we have a valid connection or after we've lost one and before a replacement has been found. So it's a poor man's message queue in the AMQP sense. Doing jam over AMQP is something we've looked at lately, but we don't actually do that yet. Many networking libraries implement an RPC mechanism. So jam doesn't exactly do that, but it can sort of pretend it does. We have a notion of registered messages and can associate specific response messages with a request we sent. In this example, we see code that's sending an add player request to a matchmaker. The template argument there indicates that we're expecting a player added message as a response. Behind the scenes, what happens here is that jam inserts an integer ID sequence into the message header, and then the matchmaker sends a reply back with that same sequence. Though the main reason for the template parameter is to make the flow clear when reading the code, we also check when we get the response that the type is actually correct. We can do that without any extra work because the message is a generated class, and one of the generated methods is a static getMessageID field method. Although a lot of our jam-based code is services and tools talking to other services and tools, we are, believe it or not, making a game. In this game, we have a bunch of objects, checkers obviously, that need to talk to each other. Sometimes our checkers live all on one server, sometimes they're spread across many servers. When we want to send a message from one checker to another, we could, of course, figure out what server the other checker is on, send that server a message that contained an ID for the recipient player, and that server could call a method on the player with the message we sent it. But that's a lot of work. We'd much rather do what this slide shows. It's got an array of checker pointers and sends a copy of the same message directly to each of those checkers. In our checkers MMO, each checker is owned by exactly one server. But checkers on different servers can still interact with each other. To accomplish this, read-only copies of checkers are mirrored to other nearby servers. Whenever one checker wants to interact with another, it can only do so by sending that other checker a message. When we receive a mirrored copy of a checker, we record what server actually owns it. As you can see on the slide in the mServerID, member. Even for checkers owned by the local server, we just put the local server's ID into the mServerID field. So one important aspect of jam, especially for messages sent to objects, is that loopback messages are allowed. In many cases involving multiple services of the same type, our code will be cleaner if we write it to always assume message passing is required. Because we can send a message to our own server's jam ID, those cases will work transparently whether the object is remote or local. So I've shown a few things calling server send methods. In programs that deal with service level messages only, there are predefined send methods built into jam. Services that deal with object-level messages typically need to implement one like this that determines from object-specific data what server the object being sent to lives on, and then calls a built-in jam method that also passes an object ID onto the receiving end. We typically write this once per service, and if there are multiple protocols handled by that service, they can all share this method. So we're sending messages, but that doesn't do as much good if there's nothing that knows how to work with those messages. Let's see how our message handlers work now. So on the receiving end, we get a link and a message pointer for each message that comes in on protocols that have been specifically registered for our service. The message object now contains the destination checker ID that the sender asked us to deliver this message to. What that means is we can look up an object, seen here in the getCheckerObject call, then call a dispatch method that will in turn call a method on that object with our message pointer. The jam checker protocol dispatch method called in the switch here is a method that was generated from our jam file. To be clear, the code that's on this, oh shoot. To be clear, the code on the slide is code we only have to write for protocols that are to be dispatched to objects rather than services. Jam will include object IDs in the messages it sends, but needs the application to look up objects to which messages can be dispatched. That's all this code does. We still didn't have to write anything here that is aware of specific message types, only protocols. And depending on the service, it might be possible to assume all messages are object messages and not even have to write a case per protocol. In reality, our main gameplay server actually routes messages to components based on the protocol, not to base level objects. All right, so you'll see some examples that pass a jam link reference around, especially to message handlers and dispatchers. Jam link is an object representing a connection to a remote application. From it, we can tell what type of app we're talking to, what protocols it supports, and disconnect it if it's misbehaving somehow. It's a really straightforward class. I just wanted to point it out so you know there's nothing magic going on when you see it. Most handlers only care about the message they get passed, but a few need more information about the sender than just the jam ID, so we pass them a jam link as a convenience. It's also possible to go from a jam ID to a jam link at any time, except that outside a handler, there's no guarantee the jam link will still exist if the application at the other end has gone away. Inside a handler, the jam link that corresponds to the sending application is always guaranteed to be valid. In the previous slides, we saw a handwritten code that understood application-specific objects and called a dispatch method. This is the generated dispatch method it was calling. You can see that it takes a templated type. We passed a checker, a pointer to that type, and a message pointer. The message contains a numeric code that can be mapped to a specific message handler. So we just call that method on the object we were passed. This is one of the big benefits of code generation. If we had to write this dispatch method by hand for every protocol we implemented, we'd be very sad. Checker, heal handler, and any other message handlers required for this protocol are methods whose bodies we define by hand, but whose prototypes are generated for us. So let's see how that works. When we run our jam files through JamGen, one of the output files is a header file that's really just a code snippet containing prototypes of message handlers. General usage is to pound include this header in the middle of a class in order to add message handlers for all messages in a protocol. I know that sounds a little bit odd, and it probably is a little bit odd. In the past, we generated pure virtual interfaces instead, which resulted in lots of multiple inheritance and a little bit of extra overhead calling virtual methods. But either approach works, and it's mostly down to aesthetics which one you choose. In either case, the generated dispatch method on the previous slide is calling the methods defined by this header. Finally, we can actually handle our heal message. This is it, just a simple class method that takes a specific message pointer type and can do what it wants to with the contents. Whenever someone sends a checker heal message to this checker, it'll get dispatched to this method, which can then update the checker's health, log some stuff, and be done. This is really the core of what Jam is all about. All the infrastructure I'm talking about today is mostly there so we can implement these methods painlessly with a minimum of redundant code. So to recap the last two sections, these two methods and one message definition are all the application code we typically have to write to handle a new message type. There is some application code that knows how to route messages to objects, but we wrote that once a long time ago and forgot about it. When we add a new protocol, we might have to add a line or two to configure that protocol in our services. We don't have to add anything to it for new messages within a protocol. We write a function that sends a message, and we write a function that handles a message. Everything else is generated or written just once per protocol, not per message. All right, so finally we're at the end of our cycle. We've written code to send and receive, but we haven't told the system how to get our messages from one place to another yet. So that's pretty easy. I'm going to show that now. Jam is based on services. In order to receive messages, we tell a jam route config object what protocols we want our jam service to handle. Jam route config takes care of figuring out when and how to call our message handlers. In the simplest usage, all we have to do is call a jam route config configure inbound with the protocol name we want to handle, and then implement the handlers for all the messages in that protocol. Prototypes for all those message handlers are already part of our class because of the generated file we found included a few slides ago. Though it's not obvious on this slide, the first parameter we're passing to configure inbound here can be an instance of any class that implements the handlers for the protocol we're configuring. Usually it's just an instance of the service, but it can be another class owned by the service if it makes more sense for the given application. So as we've seen, when we're setting up a program's protocols, we have a route config object, and we hand it protocol to handler mappings. For each mapping we give the route config, it creates an instance of an object that can dispatch messages on that protocol to the handler class type. By using templates here, we don't need virtual interfaces nor more generated code, although of course templates are just another way to generate code. When a message is received, route config figures out what protocol it's a part of, a little more on that later, what handlers are available for that protocol, and how those handlers want those messages dispatched. I'm saying handlers, but the slide says services. Most of the time, a service registers itself as the handler for a given protocol, but that's not required. A different object can be set up as the handler if it helps make your service cleaner or otherwise makes sense. So besides the raw message data, each handler is passed a jam link reference. From the jam link, we can determine lots of things about the sender, such as what type of program it is. We have an enum that currently contains 45 to 50 different entries for all of our applications. Each entry in that represents one app. A subtype that's defined on a per application basis, and even some more specific stuff like map IDs when appropriate. Of course, I mean board IDs, because Checkers has boards, not maps. Of course, the most important thing we get is the sender's unique jam ID so that we can send them a response, track the request for later if it requires some async work, do authorization checks, or anything else we might want to do based on the sender. I mentioned that the simplest use of jam route config is to simply let it manage when and how we receive calls to our message handlers. That's sort of true, but due to its roots as something used only by high-performance game servers, particularly multi-threaded ones, the simplest behavior doesn't actually do any thread synchronization for us at all, and it can and will call message handlers simultaneously from multiple threads. It does guarantee messages from the same sender, never processed concurrently, though. That's really not what you want for the majority of applications, and we have several other options available. The easiest way to deal with receiving jam messages is to give route config a message queue object for our service during configuration. It's there. Then we process that queue only at a known time on a single thread. That pulled model is perfectly fine for the majority of our tools and servers, and even for our game client. It's the preferred model anywhere where ease of use is more important than latency or throughput. So in this slide, we see some code that tells our route config to put messages for any of our supported protocols into a single queue. And then in our idle method, we ask our jam server to process that queue. mMessage queue in this case is a jam message queue object, which is essentially just a linked list with internal locking that makes it safe for messages to be enqueued from any thread and then swapped into a local list for processing later, which is exactly what process queue does. All right, though I generally prefer to split servers into multiple processes rather than multiple threads, there are a few cases where having more threads makes more sense. There's two main strategies for these servers. One is to have a global lock in our service, which route config knows how to acquire and release, so that although our message handlers get called from multiple threads, only one of them is actually active at a time. While this makes it essentially single-threaded, it does have the advantage of not having to copy messages as much in some situations. For services that don't need a lot of concurrency during message handling, this method makes a lot of sense. It's also possible for services to manage locking themselves and not let route config do anything about it. Most of the time, that's the scary option you don't want to use. Though jam will do the right thing as much as it can, this creates all the usual concurrent headaches in your service class as messages are handled directly on a network thread with no guarantee you don't have other code running on another thread. How to deal with those kinds of concurrency issues is a whole other talk, and I'm not going to be going into it today, other than to say that's what happens if you're not really careful with that method. Finally, services can actually create locking policies of their own and hand those policies to route config to handle locking on a per message or per protocol basis. This can be used to, for example, acquire a read-write lock thread, read-write lock in either read or write mode depending on the message being handled, or handle some messages immediately and defer others based on any application logic we want. The global lock strategy I mentioned earlier is actually just an implementation of a lock policy that acquires and releases a single mutex for any incoming message. And since we pass this lock policy into the system as a template parameter, it doesn't need a base class. It just needs lock and unlock methods with proper signatures. So a few last things on receiving messages. The incoming message is actually a ref-counted object. If a message gets to our handler, but we need to hang on to it for later because we're not ready to process it or we have some async I/O to do, then we're completely free to do that as long as we retain a reference to it. We have smart pointer classes for dealing with that, so there's not usually any problems with leaked messages. Messages don't contain references to anything, which means there are no circular references possible. Though most services handle messages immediately and don't retain them, that flexibility is very handy for the few services that need it. In several cases, it's let us avoid re-implementing queuing systems elsewhere by simply retaining a list of pending messages which we weren't able to process immediately. Since we're making a game and every cycle counts, we're also very concerned with how efficient our code is. Since we're also making MMO checkers and planning on hosting the servers ourselves, bandwidth efficiency is also important. So I'm going to show you how Jam achieves those goals now. If you've dealt with the problems Jam attempts to solve in the last 5 years, you've probably run across things like protocol buffers or thrift or Avro. All those in Jam are in a similar space, but Jam's main differentiating feature is speed. Jam was originally used solely between game servers on World of Warcraft, and some of the scenarios it was used in were frighteningly high bandwidth, though at the time not over the internet, all within one data center. Also, it was always safe-ish to assume that anything you connected to was using the exact same protocol, since servers for any given build were all deployed together. So back then, Jam strove only for high performance given pure binary compatibility. What it sacrificed was inter-version compatibility. There wasn't any. Once we started using Jam for tools and other things, things other than just game servers and clients, we quickly started having problems with having to synchronize our deployments of everything. So I'm going to show you how we address that. The first step to fixing incompatibilities between versions was to actually detect versions. JamGen today has the ability to create a CRC of each protocol it generates. If a protocol has all the same messages in the same order, the order is important because we use numeric message IDs determined by the order they appear in their Jam file. And they have all the same fields, then the CRC comes out the same, and two services using that protocol know their versions of it match exactly. They know that because the very first thing we send to the other end of a connection is a list of protocols we know and how to send list of protocols that we know about and their CRCs. In this case, Jam knows it can use good old-fashioned, fast, efficient, pure binary serialization. That's the case we expect to always hit for game servers. Because the wire format is so close to the structure layout, there are actually cases where we can simply memcopy a message onto the wire. So when I say we, unlike most of the rest of this talk, I actually mean WoW. I'll point out one thing here, which is that there are actually two slightly divergent versions of Jam at Blizzard. WoW and Titan, sorry, I'm not supposed to say that word, split off at one point. So they share a common, the code shares a common ancestor. And the mem copying a message onto a wire is a case where WoW has added functionality we haven't picked up yet. So if JamGen can detect structure layouts that match the wire format and protocol negotiation can detect that our endianness matches, then we can simply copy messages and not even bother with serialization. Because we generate all of our serialization code, we can immediately take advantage of new optimizations across many different protocols at once. This is true for both bandwidth and CPU optimizations. For example, you might have seen a few slides back that our binary encoder is doing a function call per field and passing a completely useless field name in. If we get smarter, we can easily generate serializers for all or some of our messages that stuff their data directly into a buffer, saving us CPU time. If we get smarter in a different way, we can create automatic bit packing serialization. Because we control the grammar for our message definitions, we can even enable options like these on a message-by-message or protocol-by-protocol basis. The important thing with all these kinds of optimizations is to do it smartly. Only when profiling bandwidth or CPU shows that it's necessary. But the nice thing about all the generated code is that if it's necessary for one protocol or message, then every protocol or message can benefit. So when two services have determined that they have binary incompatible versions of a protocol, that triggers a switch to JSON serialized Jam. JSON is great for programmers. It's easy to look at anything encoded in JSON and see exactly what's in it. Unfortunately, it's way more expensive in bandwidth and CPU than our binary protocol. So we never allow JSON fallbacks on a public-facing protocol. And even for some internal tools, it's not entirely reasonable. Because all the data is sent using name-value pairs in plain text, it makes it very easy to take data sent from a different version of a protocol and fill out a structure in the current version. If there are fields that aren't present, they can be set to default values, and if there are fields we don't know about, they can be safely ignored. Even if fields have changed type, we can still deal with it in many cases. Okay, so in case anyone doesn't know what JSON is at this point, that's what it looks like. It stands for JavaScript Object Notation. It's just a way of expressing data as dictionaries and arrays. It's fantastic for humans, but not so great for computers when efficiency matters. So for our game client in particular, we enforce a matching protocols only rule. If the protocol negotiation that handles at link up determines that the other end doesn't match on any protocols, we treat it as an error and don't allow the connection. This functionality is exposed as a flag passed into route config. On this slide, you can see how Jam internally figures out protocols and channels. When a new connection is established, each end immediately sends a list of all the protocols it supports with names, CRCs, and whether it's willing to send or receive or both for each protocol. Its peer then checks if it's willing to receive each message the other end is willing to send, and vice versa. Each protocol where a send-receive match is found is then deterministically assigned a 1-byte channel ID. So yeah, we're limited to 256 active protocols on a given connection. You would think that wouldn't be an issue. We're up to 50 on one of our connections now, so I'm not entirely convinced. The ID is based on the order in which the protocols were found in the metadata. And we use the listen versus connect status of a connection to determine which metadata takes precedence. In future communications, that channel ID is used to determine which protocol each message sent belongs to. So our overhead for sending a message is a size, which is 1 to 3 bytes, 1 byte for a channel ID, 1 byte for a message type, and 2 bytes for a message ID within the protocol defined by that channel. In the case of an object message, there's also a 128-bit object ID, which I'll note that we don't use any object messages on public-facing protocols, only on internal ones, so we can afford the bandwidth a little bit better. The message type is always either a service message or an object message for application messages. Internally, Jam has a few more types for protocol negotiation, pings, and other connection management. So having the ability to run services with different versions of the same protocol has allowed us to create an environment where we're not locked into synchronized updates. We have an asset pipeline with many custom tools and services, and we're free to add features at the protocol level at any time. The downside of this is that when we deploy a new version of a service that implements a high-volume protocol, performance may suffer significantly. There are only a handful of cases where it really matters, maybe only one where it's extremely important, but it's almost too easy to make a change in one of those cases without realizing it. You can see from this chart that even for small, simple messages, JSON serialized messages can be 3 times larger than binary or worse. Despite the drawbacks to JSON fallback, it's been a highly successful means of keeping our build process sane. When we have new features in our back-end servers that require protocol changes, we're able to make those changes, deploy new versions, and keep everyone working without downtimes or required updates. Though we have a good tools deployment process, we're also still a project under heavy development, and letting people stick with old versions is sometimes important. We're averaging 11 builds a day for reasons that are a completely different talk, and sometimes latest is not greatest. I've talked a lot about how we solve this problem, but we're not the only ones to take it on. Back in 2001, when I started working on Jam, there wasn't a good alternative that I knew about. Luckily for you, there are now several. Google Protocol Buffers is a popular choice. We've even used it for some projects at Blizzard. Facebook's Thrift is another good one, as is Apache's Avro. And if you're struggling with serialization issues, you can do much worse than any of those projects. All 3 of those offer a binary serialization protocol that also solves the problem of interversion compatibility. What that means is that they're all relatively bandwidth efficient while still allowing you to deploy newer versions of your protocol without fear of breaking things. Their priorities are a little bit different than Jam's historical purpose, though. Jam was intended first and foremost to be a highly efficient protocol between servers where version matching was a given. Protobufs and the others were designed to be used in environments where it was a given that there would be services that never matched and might even be years out of date in some cases. I think for many of us here today, working on games where speed still matters, a jam-like approach is still appropriate. And I don't actually know a good open source alternative with the same priorities as Jam. So here's some benchmarks of equivalent protobufs and jam messages. The left chart are times in milliseconds for some typical serialization tasks. And the right-hand chart are byte sizes for one message in two different scenarios. Even though protobufs has a small overhead beyond the pure binary data, in order to provide enough metadata about serialized messages for different versions of the same protocol to work, it can actually be more bandwidth efficient than Jam. The reason for that is smart integers. Protobufs has a method of sending integers where smaller integers take fewer bits to send. For example, a 32-bit int whose actual value is 5 will only take up 1 byte on the wire. We don't do anything like that in Jam at the moment, though, of course, because we control everything, it's something we're certainly looking at adding. In practice, for well-built protocols, protobufs doesn't very often achieve that result. And a potentially large disadvantage of protobufs is CPU. When we benchmarked protobufs versus Jam, we found protobufs' default C++ implementation to be 3 to 5 times slower than Jam at serializing and deserializing in virtually all cases. That was really surprising to us, but I'll note that there are several alternate implementations that may be faster than Google's. And I haven't done the benchmarks on the other libraries I mentioned. If you're looking into using or setting up a system like Jam, some of those alternate implementations are definitely worth looking into. So when I started writing Jam, I didn't have any alternatives. Though there are some reasonably good partial solutions out there now, there's something to be said for doing it yourself. Though I've only scratched the surface in this talk, a system like this isn't actually all that hard to create. If you're struggling with data serialization or message delivery systems, you owe it to yourself to find a solution. Your generated code can be just as fast or faster than hand-rolled code, and you can easily achieve cross-version compatibility. All this means we spend less time on the boring parts of network programming and on debugging, and more time on making our game awesome. So, thanks everybody for coming. Thanks. Thanks. Looks like we have time for questions. Microphones are in the center.
So I've used code generation. I love code generation. But for serialization, how do you feel about using reflection, building a reflection system into your code, and then just letting classes kind of self-describe their own data and just interrogating them and asking them what to do?
So when you say building reflection in, so it's C++, do you mean using RTTI or building something
building something that's doesn't suck.
Okay. Yeah, I agree with that. No, we don't use RTTI for anything either.
Good.
Yeah, that's not a bad approach. I think that could actually work pretty well. I think C++11 might even make some of that easier these days. So yeah, a lot of this code predates people even talking about C++11. So yeah, I think that could be a workable approach too.
Hi. About that graph, comparing size, serialization times between Jam and protobuf. Yeah. Is Jam in that case doing binary serialization?
Yeah,
or it's an average of both approaches?
This was binary serialization.
All right, so you have no stats JSON against protobuf?
Right, yeah, I didn't worry too much about our JSON serialization. I mean, we try to make sure we're using binary whenever we can.
So it doesn't even average when you have to default to JSON. It doesn't treat JSON at all.
Right. Yeah.
All right. Thanks.
Okay.
Maybe this isn't the kind of thing you guys are considering, but have you had any thoughts about open sourcing Jam?
I've certainly had thoughts about that. That might happen someday. I mean, that would take some effort on my part, and then I have to go through legal and say, hey, can we actually do this? I would love to do it.
Awesome.
I'll keep you guys posted.
Cool.
Thanks. All right, nobody else? Okay, thanks for coming, everybody.